Here's a puzzle. You sum a million integers stored in an array. It takes 3 milliseconds. You sum the exact same million integers stored in a linked list. It takes 42 milliseconds. Same numbers, same total, same CPU, 14 times slower. Why? The answer is cache memory. And once you get it, you'll write faster code for the rest of your life. Start with an uncomfortable truth. Modern CPUs are ridiculously fast, a few billion operations per second. But main memory, your DRAM, is not. Fetching a value from RAM takes around 100 nanoseconds. In that time, your CPU could have done 300 arithmetic operations. That's the memory wall. If every load went all the way to RAM, your CPU would spend most of its life waiting. The fix is the cache. It's a tiny, fast chunk of memory that lives right next to the CPU core. When your program asks for an address, the CPU checks the cache first. If the data is there, that's a hit, and it comes back in about 1 nanosecond. If it's not, that's a miss, and we pay the full 100 nanosecond trip to DRAM. L1 cache is kilobytes. RAM is gigabytes. The whole point of cache design is make hits common. Here's the trick that makes caches actually work. When you miss on a single byte, the cache doesn't fetch just that byte. It fetches a whole cache line, typically 64 bytes. So if you ask for byte 0, you also get bytes 1 through 63, essentially for free. This is the key insight. Memory moves in blocks, not in individual bytes. If your next access is to a nearby byte, it's already sitting in the cache. Now the array versus linked list puzzle solves itself. An array of integers is one contiguous block. Each int is 4 bytes, so 16 of them fit in a single cache line. You iterate the array. The first read misses, but the next 15 are free hits. One miss per 16 elements. A linked list is the opposite. Each node is allocated separately, scattered across the heap. Every next pointer sends you somewhere new. Almost every access is a miss. That is the whole story. Your turn. You have a two-dimensional array in C, stored in row major order. Which loop is cache-friendly? It's A, iterating rows on the outside, columns on the inside. Row major means elements in the same row sit next to each other in memory, so the inner loop sweeps through a single cache line before moving on. Swap the loops, and you jump by a whole row on every read. Catastrophic miss rate. Cache memory isn't a detail. It's often the difference between code that flies and code that crawls. Keep your data contiguous, walk it in order, and let the cache do the work.